In this recording, I'm going to show you how to manage your lab calculation. So let's get started here. Basically what you have is an RC circuit, so let's sketch that. There's a source Vs, a resistance R, and a capacitance C. We have VC, and let's put here an IC. And what we can do is we can just write a KVL loop around here. So you could say Vs is equal to ICR, because the current goes from left to right, so ICR is the voltage there. ICR plus VC. If you like, you can put VCT. And because we know that VC is CD, sorry, that should be an IC, CdV dt, why we can write this as RC dVC dt. And so now we can write this as a differential equation in our standard form. So let's write it like this. Vs over Rc is equal to dVc dt plus 1 over Rc VCT. And earlier we gave you another general form where, you know, we said, okay, this will be 1 over tau. And if we said, okay, well, this is dx dt, we're identifying Vc as x of t, and x of t is the solution, by the way. And this we're going to say is the forcing function, f of t, but in this case it's just some constant. So what we have here is a general solution, actually. When the forcing function is a constant, I'm just going to tell you that the general solution, x of t, is going to be some constant plus an exponential divided by tau. Okay, so here tau is equal to Rc. And how do we find out what A and B are? Well, let's just write this out. To fully specify x of t, we need to find A and B from initial and final conditions. Okay, so how do we get initial and final conditions? Well, we'll just start thinking about this here. The circuit that you have, well, you have V of S, that's a square wave, basically. So let's draw that in there. Starts at 5, goes down to 0 volts, back up, so on. Let's say this is some switching time. We'll call it T1. Let's call this T0, T1, T2, so on. And basically you can think of it as like this. You have a circuit. Let's sketch a circuit that is, think of it as a source. In fact, let's specify that it's a 5-volt source, and then there's right beside it there's a short circuit, And so now we have a switching circuit that, let's say that in some points it can be in position A, where it's connected to the short circuit, or position B, let's make that a B, where it's connected to the 5-volt source. So here's what we've got going on here. And let's just see how this applies now. So this x of t over here is actually going to play the role of our v of t. So let's just make a note here. Vc of t. And we're going to use steady state analysis to determine what the initial and final conditions are. So let's start with initial conditions. So let's say for initial conditions we're going to think about time less than t naught as we approach t naught. So what we're looking at is this region here. So we're dealing with switch position A. And in switch position A, let's assume that the circuit is in steady state by the time that it gets up to t naught. So steady state, let's sketch the circuit, and we'll put in here, well, it's a short circuit, an R, and then in steady state the capacitor is like an open circuit. So we'll put Vc, we'll put here T0 minus, and what you can see here is, well, the current is 0. That means that this voltage here is 0. And so if you did a KVL loop around here, well, you have 0 plus Vc is equal to 0. So there's our initial condition. And let's put in a final condition now. We're basically thinking about this region. Oh, let's switch colors just for clarity here. Let's go to a blue. Now we're thinking about this region. We've got switch in position B, and let's just say that the circuit, see, it has no idea that the switch is coming at T1, so we're just going to say that as T goes to infinity, or T greater than T naught, with T going to infinity, we have this circuit, right? So we've got plus minus 5 volts, and then we've got R, and in steady state the capacitor is like, again, an open circuit, so plus minus, and this current here is 0, so this voltage has to be 0, so Vc of infinity has to be 5 volts. Okay, so that's great. Now we are going to plug in our general form. So I'm going to erase some of this. Okay, so just looking at this right here, we're going to say, all right, our general form is that Vc of t is A plus B e negative t over tau. And so we're going to use our initial and final conditions to figure out what A and B are. So let's say, okay, t equals 0, or t naught, let's define t naught as 0. So we know t naught is our 0, and we have, okay, Vc of 0, then, looking down at the green circuit for the initial conditions, we have Vc of 0. We said, oh, hey, that's 0 volts, and that's A plus B. that tells us that A is equal to negative B. We still don't know anything more about them. Now if we use the long-term condition, the long-time condition, the VC at infinity, we said that's 5 volts, and if you plug in infinity for this general form here, for negative t, for the exponential goes to 0, so we're left with 5 equals A, so A is 5 volts and B is negative 5 volts. And so now we know, okay, VC of t goes from 0, starts at 0, and then rises to 5, rises to 5, so we'll write this like this. Just, we know, since we know A, we'll put 5, and then B is negative 5, E negative t over tau, where tau, as we said, is RC. I said that earlier. Okay, and if we were to sketch this, it would look like this. Here's 0, it's VC is in volts, and it starts at 0, it rises with an exponential form asymptotically to 5 volts. And here's t on the x-axis. And what we're going to say is, at some time, 5 tau, you could do the math, but at that time 5 tau, VC of t, we say VC of t is approximately its asymptotic value, so it's 5. It actually reaches 99% of the asymptotic value by that time. So that's what we've got going on, is when the voltage input goes from 0 to 5, then this capacitor rises like this, it's charging up to 5 volts, and it has an exponential rise. Now, the next thing for us to do is to consider what happens when we switch the circuit back. So I'm going to erase some of this, and we're going to define a new time, t1, to be like our 0. We can do that, that's okay. Okay, so let's go with t less than t1, and now we've got circuit B, so what we have in steady state, we have circuit B. Okay, so we did this, we said, okay, this is 5 volts, VC is 5 volts, all right, and for t greater than t1, let's say that if we're calling t1 0, then let's let t approach infinity. Not 8, let's do infinity. Okay. Then again, we have this short circuit R VC, and we said, hey, that's 0. Okay, so here's our initial condition. We'll put VC T1 minus, okay, we'll say, hey, that's 5 volts, VC, let's say T minus T1 is infinity, goes to, whoops, how do we want to write that? Let's just write it as VC of infinity goes to 0. Okay, so I'm going to erase some of this, and we're going to do what we just did before. We're going to apply the initial conditions. So we'll put a red line here, and the initial conditions and final conditions will help us to find the new form. So let's write. We have a new time segment. So VC of t, where now t1 is our 0. It's a. Actually, let's use different symbols. So f plus g e negative t over tau. Okay, so we said VC of 0. This is our VC of 0 right here. It's 5 volts. 5 volts, and it's f. And you put in 0 for t, the exponential goes to 1, so it's f plus g. Okay, and then VC of infinity, we said is 0, and that's f. Okay, so this tells us then that f is 0, so g is 5 volts, and so we have, I'll write it here in red, for our new time segment, VC of t is 5 e negative t over tau. So the previous one, let's just make a distinction here. This is, let's put here t, let's go from t0 less than t less than t1. And then for our red equation, we can just time displace it, time shift it. So how do we do that? We just say, okay, we'll put VC of t is 5 e t minus t1. There's our time displacement over tau. And if we were to combine these, I'm going to erase this now. If we combine these, why, we get something that looks like this. Let's make a plot of VC of t. And we get something that starts at 0, rises exponentially. There's our t0. And then at time t1, it falls exponentially. And let's say that it rises up to 5 volts. Let's just put in a label here. And then at some time t2, we again flip our switch, or the unit pulse changes, the square rectangle, or square function, square wave. And now we have this sort of thing again. Now, let's continue on with our 5-volt marker. And we said that, hey, the voltage reaches its asymptotic value, or we say it approximately reaches its asymptotic value at 5 tau. And you could imagine using different values of R and C. Let's put in here, I guess the second, we don't know that that's really 5 tau. We know that this is 5 tau, and this is 5 tau. Basically, 5 tau is the time it takes for the RC circuit to settle down, or the exponential part to decay. And I guess what I'm trying to say here is that we start to run into trouble when 5 tau is greater than half the period, right? Because the period of the input is t2. Here's the period. And so t1 is half the period. But if t1 happens before 5 tau, then the capacitor won't fully charge, and then it starts to discharge, and so things, basically the capacitor can't keep up with the input is what's happening there. If you can see, I know it's kind of hard to imagine, but that's what I have for you. So we start, because like I said, tau is RC, so you could imagine using different values of RC, R or C, that make the circuit too slow for keeping up with the unit step input. So that is what I wanted to show you in terms of the theory behind the pre-lab. I hope you found this helpful. That's all I've got for you today.